So hey everyone, today we will be covering the different file formats in big data or Hadoop in a lot of detail. Before I jump into detail of different file formats, so basically the question is, why do we need different kind of file format, right? So whenever we want to talk about file format, we need to answer 4 types of question, right? How easy is the file format to query? What is the query time? Is it when we query a file, is it incurring too much latency? Are file easy to serialize? Data serialize should not incur much latency. So basically, when we talk about these 2 points, right, we are talking about latency. So what latency means? That once you send the request to some file or some system, when you're getting the response, right? So this particular section is called latency. So what we need from any file format, that the latency to read and write the file should be minimum. Okay. The next question what we ask about the file is the file splittable, right? So what splittable means, let me cover in a lot of details. So see, in Hadoop or in big data or in Spark, where are we working on? We are working on distributed system, right? So in distributed system, what we know that let's say if we talk about SDFS, right? How our data system looks like. Our data system looks like this. So we have one name node here, right? And then we have different data nodes. Data node 1, data node 2, data node 3, and so on, right? So basically, we have data stored here into blocks. Everywhere there, and there's some replication. There will be block 1, block 2, block 3, everyone, right? Now the question arises, how do we process the data? So this is storage. This is storage. Once we store the data, obviously we want to process it. And we process the data using some distributed computing framework like MapReduce, like Spark, or different kind of computing framework, right? And now when we talk about any computing framework, in MapReduce, we have mappers, right, and reducers. And these mappers are working on different blocks of data or different partition of data, I can say. In Spark, we have partitions, right? So basically, what I want to prove here, that the data on which we want to work on or the processes want to work on should be splittable. Now, splittable means what? Let's say we have a text file. How text file looks like? Text file look like this, something like this. Let's say, hi, I am Nilendra. Then we have a control and character, that's line and character, and I am teaching file format for you guys, and then some control and character, right? So what we can see here, this file, let's say we have 1 million like 1 million lines like this. Can we split this file? Obviously we can split this file, right? We can give this line to mapper 1, we can give this line to mapper 2, and so on. Let's say we have 1000 mapper, we can split this file into 1000 mappers. So we can say the text file can be splittable based on control and character, means end of line character, right? So whenever we find the end of line character, we can count the number of lines and we can give this number of line to some mapper or to some reducer. It means text file is splittable, right? Now let's see other file format. Let's say JSON file format. How JSON file looks like? Something like this. You have tags. So let's say tag 1 is name, and then the value is Nilendra, right? Then profession is, let's say, teaching, something like this. And then let's say salary, and then we have 1000 here, and so on. Tag value, tag value. Can we split this file? No, because let's say this is first record, and we have 1 million records like this. And if we split this record partially, so it will go to mapper 1. This partial record will go to mapper 2. Now mapper 1 will process this record. Is the result of this particular JSON file, which is splitted wrongly, when we process through mapper 1, is the result correct? No, because we haven't splitted the file properly. Half file goes somewhere, half file goes somewhere. even we don't know the logic of this splitting. We don't know. So we can say the text file is splittable, but JSON file is not splittable, right? Now same applies to XML file. How XML file look like? It's again something like this. We have text, header, footer, and then we have some value here, right? So this is tag 1, this is end of tag, and this is some value. And then we have these tags like this everywhere. And we don't know how to split that file, because obviously if this is one record from here to here, we don't know where this record starts, where this record ends. So what we can say that XML file and JSON file are not splittable, because we don't know where to start or end those files, right? So this is why we need to decide whenever we want to go for file format, we need to ask few questions to us. What latency we can tolerate, like read latency, write latency. Is the file splittable, right? And the fourth question is the file format support compression, right? Now, compression means, can we compress the data so when we store it, it will take less amount of space to store the data, right? Now, once we talk about compression, right, let's talk about two things before we go to compression. Let's talk about this point, serialization. So how easy is the file format to serialize? Let's answer this question first. So when we talk about serialization, so what serialization means? So basically, let's say if I'm writing a sentence, hi, how are you? So you guys can read this data, right? You guys can read data and you can understand this data. But is my machine or is my program will understand the data? No. So to make our program understand this data, what we need to do, we need to serialize this data, right? We need to serialize this data, and then we need to store it somewhere, maybe in memory or maybe in file disk, and then only our program will understand. So serialization means convert your objects into bytes, so that they can be transferred over network or can be stored in some file directory. Simple, right? So serialization. But now the question arises, so once it is serialized, it is stored to some file and you want to read it now. So basically how serialization works, in very simple term, it works like this. So you have one system, you have your source system, right? Which writes the data to here. And then you have a target system which reads the data from here. So here you will serialize and here you will deserialize, right? So one question is very sure, and this is, let's say, your file system. So one question is very sure, that any data which is serialized needs to be deserialized. And obviously overhead for serialization and deserialization is the overhead for the system, because we as a end user are not worried about these two things. But system, to work with distributed system, to transfer this data over the network, we need to go through it. So now we need to make sure how easy the file format is to serialize, how fast it is, and a lot of things. We will cover it, but this is what serialization means. So we have covered how many questions? We have covered splittable, we have covered serialization, and we will be covering compression in 2 minutes. And we have covered file format to query and latency about it, right? Now one more important thing. When we talk about JSON file or XML file or text file, everything is stored as a string. Everything is stored as string. So for example, let's say this is my text file, abc.txt, right? And I write in this text file 1, 2, 3, 4, 5, and then I write comma Nilendra, and then I comma this. This is comma separated file, CSV file, right? We can see CSV file. What do you think? How system will infer the record, or how, not inference, but how system will store the record if this is text file? By default, everything in text file is a string. So this is string, this is string, and this is string, right? And now what I need to focus here, that to store the string, every character will take 2 bytes. But to store the integer, to store the full integer, it takes 4 bytes. So here, how many bytes it will take? 1, 2, 2, 4, 6, 8, 10. Just to store this number, it will take 10 bytes. But if we store this particular thing as integer, it will take only 4 bytes. So this is the drawback of text files. Everything they stored as by default as string, and that's where this whole thing, they will take a lot of memory to store it. So this is something about text file, right? What are the benefits of text file or XML file or JSON file? They are human readable. They are human readable. We can read them easily. What are the drawbacks? That okay, they store everything as string. They are not space, efficient. Lot of things, right? So now let's move ahead. So we know that whenever we want to select the file format, we need to answer 4 questions. And now let's see how different files and what are different files and where those different files fit in these questions, right? Let's see. So, and this is important. Basically, integer is stored at 4 bytes, and every character is stored at 1 byte, and short is stored at 2 bytes. And in text, everything is stored at character or at short, right? So, and why do we need splittable? Splittable file allows processing to be distributed over multiple worker nodes. I have covered it, right? Okay, this is important. So let's say we have some data, and forget about big data, forget about Hadoop, Spark. In a very simple machine, on your hard disk, how data is stored? Data is stored on a disk, right? Data is on a disk. And how we read data, let's say when I'm writing select star from table name, or when I'm let's forget about select star. When I'm watching a movie on VLC media player, how movie is getting displayed on my so basically it is stored on disk, and on disk it's stored on sectors. So basically we have, on every disk we have a head, right? And let's say we want to view this particular data set. We can only read this data if the head is present on the top of the data. So this is our disk, this is our head, something like this. If we want to read this particular data, then our head need to move here and head to cover this, right? This is how the data processing or data storage work. Simple. Now we came to know that okay, on disk the data is stored, and when we need to read the data, the head needs to move to that position. So now on a very, very simple word, right? And again, don't focus too much on big data. On a very, very normal term, let's say I want to read Nilendra from disk, and my name is stored like this, Nilendra, and my disk is here. And so basically I need to read Nilendra. So obviously disk from here needs to travel all the way here, and this is again in real world it won't work like this. I'm just telling you. Then it will go here, it will go here, it will go here, it will go here. So what we can see, that this is called disk seek time. This is called disk seek time. In this particular case, when your data is staggered, the disk seek time is very high, right? Because your disk head needs to move again and again. But if my data is stored something like this, on a single sector or single space, something like this, Nile, one second, something like this, and my disk is here. So my disk head can come here directly and read the data. So what we can say, that to read the data fast, efficiently, it is better to store data on a single place so that this seek time can be prevented, right? In database language, it is always preferable to skip the full table scan. So let's say I have 1 million names stored here, and I only want to see the records for Nilendra. So what it is preferable that all the Nilendra's records should be stored somewhere on the common location, so that my disk seek time can be prevented. So this is how the data has been processed on disk, right? So now we came to know 5 things in total, that few file structures are splittable, few files are structure not splittable. Whenever you want to read data from the disk head needs to be on the top of the data so that it can be read. Disk head reads the data on your behalf, right? Now, so let's say, so this is clear about disk head and row, right? So let's say you have, and for everyone in this group, right, whoever joined this session, everyone know that whenever we talk about relational database, we have columns and we have rows. So data is stored in columns and rows, right? So basically here, how many columns we have? 3 columns. How many rows we have? 4 rows. And how many values we have? 4 into 3, that is 12, right? So now the question arises, how we can store this data onto the disk. So we cannot store the data as it is. We cannot store it. Either we need to store it row by row or column by row, column by column, right? So that's where the 2 type of storage or 2 type of orientation, storage orientation comes in picture. So basically we can store this data in 2 ways, right? Row oriented or column oriented. Row oriented means what? So this is your first row. This is the first row. So we'll store this row here, and then we can store the second row here, third row and fourth row. So this is your row oriented. Let's move ahead so it will be more clear. This is how the row oriented layout will looks like. So what we do, we took the first row here, we stored it here, second row here, stored it here, third row and fourth row. So what we can see in the row oriented, that okay, data has stored row by row. Data has been row by row. We'll focus on why and when we need to go for row oriented, but this is the first way of storing the data. What is the second way of storing the data? It's very easy, column oriented, right? So what we can see here, that this is how the row oriented work. But this is your first column. This is your second column. This is third column. Can we store the column one by one the same way we store the row? Yes, we can store the data like this. This is how your column oriented data will work. So what these guys get? 1 4 and column 2 2 5, and this is, see what these guys did, that they store the data column 1 column 2 column 3, column 1 column 2 column 3, right? So if I go a bit high, column 1 column 2 column 3, and 1 second guys, yeah, so column 1 column 2 column 3, and then column 1 column 2 column 3. So this is how your column oriented data will work. Now let's see the practical example, how so data will be stored in column and row oriented. So let's say we have this particular data in which we have symbol, Tesla, price, date, created by, exchange and time. Okay, so we have how many columns we have? 1 2 3 4 5 6. How many rows we have? 4 rows. Okay, now let's see how this data has been stored in row format and column format. Okay, so when we go for, 1 second, yeah, so when we go for row format, so what actually row format figure is not here, but row format will be stored something like this. This row will be stored first, this row will be stored first, second, third and fourth, right? But how it will store in column format? Column format will store like this. So the first column will be stored here, the second column will be stored together, the third column will be stored together, fourth column and fifth column will be stored together. We know this thing now. Okay, now one thing is very clear, and let's jump to this section because this is most important thing. So we know one thing, in row format we stored, see, let's forget about row format and column format of one thing. But in table, how things work, this is your table. This is your, let's say I'm talking about you guys. So this is your ID, 1, 2, name Nilendra, Akash, something like this. And let's say name and salary, 100, 200. We know one thing, that in one particular row, we have data about one particular ID, full data. So when I talk about ID1, I know the ID1 belongs to Nilendra, his salary is 100, ID2 belongs to Akshay, and his salary is 200. So if I want to have the complete information about the data, so let's say if I want to know everything about Nilendra, I can write something, select star from, let's say this is table 1, where ID is equal to 1. What this will give me? This will give me everything about ID1, right? So if we want to select everything, about data, we will go for which storage? Row format. Because in row format, data stores like this. First row, full 1, 2, 3. Then it will be second row here, right? 1, 2, 3. So, and now let's see how disk head will go. So let's say it will go to ID1. ID1 is here. It will go to select star. Select star means the first full record. So disk head will start from here. It will go till here, and it will return me the result, right? So it means if we want to go for full record, then we will go for row format, because in that particular scenario, your disk head do not need to seek a lot, right? Now, let's say if I'm only selecting salary, I only selected salary. So here I'm selecting salary. For ID1, I need to select salary. On, let's say I want to select salary for everyone. Select salary from table 1 for everyone. If it is stored in row format, how it will work? This is my salary column. So it will go here, pick 100. It will go here, pick 200. So how it will working? Disk space or disk head need to jump from one section to another section, and then to another section, then to another section, where we store the salary. So is row format beneficial if you want to select one column? No. Is row format beneficial if you want to select all the columns? Yes, right? So in very, very simple term, and again, see, again, this is nothing related to big data. This is the basic understanding how data stores. So when we want to select all the columns or all the data, then we will go for row format. When we want to go for specific columns or selected columns, then we will go for column format. Now, the same example. We have 2 rows here. One, let's say this is ID, name, and salary. One is 1, 2, Nilendra, Akshay, 100, 200, right? This is my raw data. Let's say I want to store it into column format. How I'll do it? 1, 2, first, Nilendra, Akshay, here, 100, 200 here. This is how it will work, right? Now let's say if I write a query here, select salary from, and let's say this is again tab 1, from tab 1. What I'm selecting here, cell. So it will, where I have stored the salary, here directly. So let's say my disk head is here. Before starting the process, it can directly jump to here. It can give me 100, 200, simple. So whenever we want to go for a specific column, we will go for column-oriented columns, column-oriented storage. Whenever we go for all the columns or full data, then we'll go for row format. Simple, right? Now, let's see how row format and column format works in real world, and how much performance column-oriented gives if you want to go for selected columns. Let's see. Okay, so with the same data sets. So let's say we have this data set. If we store this data set into column oriented format, and let's say we have 1 billion records. Let's say these records go till 1 billion, right? And assume each record is of 100 bytes. So it means the first row is of 100 bytes, second row is of 100 bytes, and we have 1 billion record like this.
So in total, this 1 billion record will contribute to 100 gigs of data, right? And let's say our internet speed is, or our speed of processing it, 100 MB per second. 100 MB per second. How much data we have? 100 gigs of data, and our speed of processing it 100 MB per second, right? So how much time it will take to process all this data set? At this speed, it will take 1000 seconds, right? In row-oriented storage, it will take 1000 seconds to process all the data, right? Now let me ask you one question. In the data has been stored as row oriented, and I only select symbol and exchange. So what I write something queries like this: select symbol comma exchange from tab 1. Let's say this is tab 1, right? How long it will take for this? Even though I'm selecting only 2 columns, that is symbol and exchange, it will take 1000 seconds. Why? Because the data has been stored as row format, right? It can, in any case, it need to go through the full row, then it will go to the second row, it will pick 2 columns, it will pick 2 columns from the third row, it will pick 2 columns. In this way, it need to go for the full table scan, right? And that's where, even though we are selecting only 1 column, 2 column, if it is row storage, row oriented storage, it will always take 1000 seconds, right? Now let's talk about if we store this data into column oriented, how it will work. It will work like this. So we have symbol stored at one location, price stored in one location, and we have an exchange stored at one location. So it will be till 1 billion, it will be till 1 billion, it will be till 1 million, and it will be till 1 billion, right? And let's say if I run the same query and select symbol, that is this section, and exchange from table. Let's say this is tab 1 again. How our disk space or disk head will work? It will go here, select everything, and then quickly it will skip this, it will skip this, it will skip this, and select this. And then it will give the data. So what we can see here, from a very raw layman term, that here 1, 2, 3, 4, 5, we have reduced the time almost by half, and that is where it is stored here. So what it says, that if we, and this is the example for 3 columns, and same applies to 2 columns. What it says, to process 100 gigs of data at 100 MB per second, and we are only selecting, let's say 3 columns, I give the example for 2 columns, it will take 500 seconds, right? So what we can see, let's say we have 6 columns and we only selected 3, it reduced the amount by 1/2. It means if to read the full column it takes 500 seconds, it will again divide the data and it will give 500 seconds. So this is the beauty of column oriented, right? Now the question arises, if in this particular case we write select star, it will be fast or slow. If in column oriented we go for select star, it will be fast or slow. So do research about it and let's see. You can comment in the comment section after this lecture. Okay. This is how the where clause work in your column oriented. So let's say I only want to select data whose date is greater than 1/1/2020. It means the records which occurred after 1st January 2020. How it will work? Okay, this is very important concept and I will cover it in detail now. So we know few things now. The data is stored on disk. When we write a query, the data will come to your processing framework or in your memory, and the data will be displayed on your console. We know this thing. So from disk head will read the data, it will write some query, and it will write the data to console. Now the question arises, let's say we want to have data greater than 1/1/2020. So what is more efficient, to filter the data here and only give the filter data back to us, or to bring all, so this is your filter data, let's say, and or to bring the full data? Which one is more efficient according to you guys? Obviously filter data, right? But can we bring filter data directly from the source? The question is this:
So can we bring filter data directly from the source rather than filtering data onto our side or onto client side? So this particular approach, when we want to push our filter condition directly on the source and bring the filter data directly to the client, this is called filter predicate push down. Push down to where? This is called predicate. Sorry, Control Z. So 1 second, guys. Sorry. Yeah. So predicate push down. Now, what is predicate means? Predicate means any condition. Into our case, predicate is where clause or filter clause. So if we push the where clause to where? To near to the source, then we call it predicate push down. And predicate push down, to be honest, is a very, very efficient optimization technique. So in column-oriented databases, or column-oriented format, what this guy did for us, it went to the source, only pick the IDs which has filter date, which has date greater than 1st Jan 2020. The IDs are 134. Then it brings prices for these IDs and symbol for those IDs. Simple, right? This is how filter predicate push down works. So filter predicate push down can be easily applied for column oriented database or column oriented storage. Okay, so see, now we know that we have two kinds of storage: row oriented, column oriented. We will go for row oriented when we want to go for full data scan, but we will go for column oriented when we go for partial data, right? So now let's go one step ahead. Okay, now which storage, according to you guys, which you worked on, not in big data but in your normal day-to-day life, are column oriented or row oriented? So text file, XML file, JSON file. So these three files which you guys must have heard of are row oriented. They always stored in a row oriented fashion. Now one special format is called Avro, which we will be covering in detail today, is also stored in row oriented format, right? Now other file format which is stored in column oriented are Parquet, ORC, and one more is RC. So these files are stored in column oriented fashion. Okay, so this is what again, in a very, very bookish language, in column oriented data is stored sequentially. Yes, CSV also. So when I talk about text file means everything: CSV, TSV, everything. So text cover everything. Okay, now let me read bookish language for you, so that if somebody asks you, you can tell in very precise way. In column format, data is stored sequentially by column from top to bottom, not by row, left to right. Having data grouped by column makes it more efficient to focus computation on a specific column of data. Reading only relevant columns data saves compute cost, as irrelevant columns are ignored. Having data stored sequentially by column allows for faster scan of data because all relevant values are stored next to each other. There's no need to search for values within rows. Column-based storage is ideally for sparse data sets having non-empty values or empty values, right? One more thing which I missed here. When we talk about compression, let's say we have data like this: Nilendra, Akshay, Soumya, something like this. Every data is string formatted. And then we have some data like this: 1, Nilendra, 2, Akshay, and then let's say some binary 0, 1, true. According to you guys, which data has, if we compress it, which data will have more compression? Obviously, the data of same type, same format, right? We can have the, and I'm not going to compression as of now, but in a very, very common sense language or common sense term, we can focus on compression if we have same type of data, because we can think about the compression technique in a way which is applicable for the same type of data, right? So in column oriented database, so how table looks like this: 1, 2, ABC, XYZ. So this is your integer, this is your string. So integer will be stored together, string will be stored together in column oriented, something like this: 1, 2, ABC, XYZ. So this is your first storage, this is second storage in column oriented. So when we go for compression, the compression is very efficient in your column oriented databases or column oriented storage, right? Because we can have the same type of compression codec or compression mechanism on the same type of data type. Okay, it's not written here, but this is important. Okay, so this is covered. Okay, now let me read one more paragraph for you. Once when we need to go for row oriented. Storing data in row oriented is ideal when you need to access one or more entries and all or many columns of each entry. For example, let's say you're presenting customer transaction history to an account manager. Account manager needs to view all the records for her client. So in this case, see, this is important. What manager wants to view all the records. And since manager wants to view all the records, which format is applicable here? Row oriented, right? Simple. One more thing which I want to cover into file format. So let's say you have your data stored something like this into the tabular format, right? You have 1 column, 2 column, 3 column, 4 column. In future, and this data has been stored in some, let's say, in some file. This is your text file. Let's say simple, comma or something like this. Nilendra, 1000, ABC, something like this. If we want to, and there are 1 million record here, in the same way, comma, 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 and this is stored in text file. Okay, so now let's say if I want to add one more column here with my father's name here, can I do it? Can I do it here in the text file, or in very, very simple terms, rather than I show you here? If I do something like this, let's say Nilendra, comma, 1000, whatever, comma, X, this, and we have records like this, and we have record so on here. That's right. And now let's say if I want to add one more column here, which says my father's name or the candidate's father's name, whatever, right? So is it very easy to add column to text file? No, right? And is it very easy to delete one column from the text file? Can I delete this column from 1 million rows? No, we cannot do it, right? So what I want to prove you here, so with every file or every file structure, we have a schema attached to it. Schema means structure. How easy or tough to change the schema is called schema evolution. Changing means evolution, right? And changing the schema means schema evolution, right? Schema evolution. So one more consideration when you want to select the file type or file storage type is how easy or tough or how much your file supports schema evolution. For example, text file don't support schema evolution, right? So which files will support schema evolution? Okay, so let's jump into theory again, and let's see the formal definition of schema evolution. Okay, so we have covered till here. So when we talk about schema in the database context, we're really talking about the organization of table, columns, views, primary keys, relationship, etc. When we talk about schema in context of individual data sets or data file, it's helpful to simplify schema further to an individual attribute level, right? The schema will store the definition of each attribute and its types. So schema will look like something like this. Let me show you one schema, and I will be covering this today. So schema looks like something like this. Let me see here, and I'll paste it here. So when we see that, okay, and forget about this. So what we can see here, that into some file, I have name of the attribute is city, type of the attribute is string, name again is state, type is string. So this is how schema will look like. So schema stored two types of information, two types of information. One is your name of the column, and one is your type of the column. Now the question is header a schema? Not 100%. Sometimes in some files, header can be schema. For example, in Avro files, header is schema, but in text file, header cannot be schema. It's a partial schema. It will only give you one, this particular attribute, only the name of the column. So header cannot be considered schema 100% of the time. Okay. Okay. So schema. Okay. So when we talk about a schema and when we want to select the file format, we need to answer 4 questions again. How easy it is to update the schema? How different version of a schema talk to each other? Is schema human readable? How fast can be schema to be processed? And what is the size on the data? Okay, let's go one by one. Updation, I talked about, like, can we delete one column and how it will impact the overall data, right? Now let's talk about this one. So whenever we talk about data in very, very simple terms, let's talk about database. So we have 5 columns today. We can have 4 columns tomorrow. We can have 6 columns day after tomorrow. So let's say we call this schema as version 1, this schema as version 2, and this schema as version 3. Now the question arises, if I have a query Q1, can that query work on all 3 versions? If the query can work with all 3 versions, then we can say that different versions of a schema can talk to each other, and different versions are compatible with each other. Okay. Schema is human readable, self-explanatory. Now the one more thing, whenever we talk about JSON file, right? Whenever we talk about JSON file, how JSON file stores the data? It is stored data something like this. So this is, let's say, my JSON file. I have 5 records. So it will store data something like this: 1, 2, 3, 4, 5. What we can see here, that with each record, it stores the schema. It stores the schema, and it's repeated. You know, like we have the same string null here, and we have the same string null here. So in JSON type, we have schema stored with every column, and sometimes we feel like that the size of the schema is more than the size of the data, and we can clearly see here my data is city here, and even the size of the data, size of the schema's data is much higher, right? So this is the last point: how much it impacts the size of the data. Can we store the schema once for the file, and then we have the data something like this? So this is schema, this is file, or is it necessary to store the schema with every record? These kind of question. Now, to answer this question, there are different types of file format come in picture, which we'll see. Splittability I covered. Okay. Now, this is important slide, so let's go through it in 2 minutes. So when we talk about file formats, right, CSV is the oldest format, which kind of evolved in 78. In 1990s, we have 2 new file format come in existence, that is XML and JSON format. Now, when we talk about XML, right, when we talk about XML and JSON, they have schema inbuilt into it. Schema inbuilt. So in 96 and 2000, people thinking about the schema and how to inbuild them in file. The only problem with this file is they are not splittable. They are very verbose. It means the size of the schema is very, very high when we compare to the data. CSV is splittable, but it don't have schema attached to it. Now, when the big data comes in picture, right? Big data means very large amount of data, millions of rows, billions of rows, 100 gigs of data. Then people started thinking in the direction how to do storage in a compact way, how to attach a schema in a more precise way. Then they come up with new type of file format, right? So the first file format which came in picture is Avro schema, Avro file, then RC file, then Parquet file, and then ORC file. And I will be covering all these files in detail. But after, and obviously in 2007, Thrift came. Thrift is Facebook, I think. Facebook is the developer of this file. Protobuf is Google. So basically in year 2007, 2008, big companies started working on file formatting, that how to serialize the file so that it can be stored in a precise way and we can read the files in a better optimized way. So there are two ways, right? So first we have some data, then we need to store it, then we need to read it. So this is called serialization, this is called deserialization. So these all techniques, protobuf, thrift, Avro, are serialization technique. How to store them and how to deserialize them. Basically, how to move the data across the network. See, when we talk about resources, and again I'm diverting from the topic, whenever we're talking about the resources, the most expensive or the most precious resource is our network bandwidth. The less data we flow through the network, the more efficient your process is. So what these people thought about, how we can compress, serialize the data. So through the network, less amount of data processes. For example, let's say if we have 100 gigs raw data, if we compress it, it becomes 2 gigs. And which is more efficient, to download 100 gigs of memory, 100 gigs of movie, or 2 gigs of movie? If both giving the same information, obviously this one. And this is where these few formats will come handy here. Avro, thrift, protobuf, RC file, ORC file, and Parquet. So after 2007, few other type of file format came in picture, which looks into above and beyond, about the storage, about the serialization, about the performance tuning. Okay, so from this particular point, people started thinking about how to process and serialize big data. Okay. Okay, I was talking to you about compression. So basically, you guys know a few things when you were, and it's not related to big data. Even in your normal Windows system, right? Whenever you go here, you have compression techniques. For example, this one. So this is zip data. When we zip the data, it compresses the file. For example, it is 694 KB. But when I go here, inside this folder, it is much more than that data, right? See, it's 2 MB, 2.5 MB. So what zip did for me? Zip compresses my 2.5 MB of data into 640 KB or 694 KB. So it means zip is one compression techniques. Okay, same way we have different compression techniques when we talk about big data. So the most commonly used techniques nowadays is Snappy. Then we have gzip, we have LZ4, and then we have ZSTD. Now, and obviously different techniques has different so basically compression, whenever we talk about compression, right, we talk about two things: compress the data and to decompress the data. So this is compression, this is decompression. So we need, let's say we want to write the file fast, then we can go for the file which has greater compression ratio, and we can write the file at a greater pace. If you want to read the file quickly, then we will go for the file format or the compression technique, which will have decompression rate higher, right? One more thing, and which is very, very important. We are working with distributed computing framework, and we want to use that particular compression technique, which is split table. Making sense, right? And that's what I have covered in a lot of detail. We can only use that particular compression technique, which is split table. So we have gzip, Snappy, LZ4, blah, blah, blah. Now let's see which, and see, it has so much detail here that, okay, compression speed is 580 MB per second, compression speed is 800 MB per second, 530 MB per second, 440. But we can only use, and we want to use that particular file format, which is highly splittable or kind of splittable. Okay, let's see which file format is splittable. Okay, this is interesting. So when we talk about gzip, is it splittable? No. When we talk about bzip2, is it splittable? Yes. So this particular technique we can use on file level compression. File level compression. There are two types of compression, right? So one is file level and one is record level. Any one of these can be used record level, because we don't want to split the record, but we want to split the file, right? So if we want to go for file level compression and we want to go for splittability, then we will go for bzip2. But on the record level, we can go for P, LZ, ZZIP, anything. Okay. This is good. So again, the same thing is written here. What is the why not store as CSV? Bad space utilization, no type or structure checking, no metadata in CSV, no native compression, no native indexing. Then other file format is okay. So now one thing we know that okay, we don't want to go for JSON or CSV or text oriented file format. We need to go for a file format which supports 5 things. It should be easily compressed, it should be splittable, it should be compressible, right? It should support some schema evolution. And people started thinking in that direction from 2007. And then they come up with different type of compression or serializable techniques like protobuf, Avro, and what else was there? One more was Thrift. Okay. Now let's see one thing, how these files work. So basically, we know one thing. In particular big data file, how many records we have? 1 million record. Let's say, I'm just assuming. And let's say this is your structured data. For these 1 million records, you have same structure. You have 4 types of column. This column is name, this column is salary, this column is age, and this column is something else. This data type is string, this is integer, this is string, this is string. This schema is common across all the 1 million records. Now people start thinking about it, what is the best way to store the schema so that sender and receiver won't, like, both sender and receiver will use this schema in some way, and so that they can code, decode, like serialize and deserialize the data in proper way, right? So let's see one thing. Let's jump to Avro. Or Avro is which type of file format? Avro is row oriented file format. Okay, so let's jump there. So before we jump to Avro, one thing which I need to show you guys. So one thing is very sure, if I have some data like this, and I want to store this data into some disk, and this is let's say this is on laptop 1, this is on laptop 2, or maybe on the same laptop, this data will flow through the network. And obviously, I have told you one thing very clearly, this data will be converted to bytes or some stream of bytes, and then only it will be stored some disk, right? This is why now we have this data and we want to store it or serialize it, and we are not using anything, we just want to store it. How it looks like on network? It looks like something like this. So we have username, we have favorite number, and we have interest. Username is Martin, favorite number 1337, interest daydreaming and hacking. So once we store it, only this small data will take 66 bytes. This data will 66 bytes. If we have 1 million rows like this, it will take 66 into 1 million bytes. So it will be around 66 million bytes, right? Something like this. So, and how this data has been stored? The normal JSON, it is stored something like this. So the first byte will tell you how many entries are there. So it will be 3 entries, right? 83 3 entries. And then the second byte will tell you what is the length of the first entry or the first metadata. It's username. Now this particular A6 will tell you what is the value of that string and what is the length of the string. This is this. So what we can see here, for each record, we are serializing or we are encoding. Let's call this technique encoding. We are encoding the value, the 3 things actually. We are encoding string, it means the type, the column value, the column name, and the column value. At the same time, we are also storing the length of column name and column value for each column. And that's where this particular technique, just to store this small amount of data, is taking 66 bytes. Now people started thinking about it. Is there a better way to store it? Then they come up with two new approaches, thrift and protocol. Let's see, and then we will jump to Avro. So in 2007 or 2008, people from Facebook and Google work on two different file storage mechanisms. So what Google did, Google developed something called protocol buffer, and Facebook developed something called thrift. Okay, and basically both are somewhere same. So how these people started thinking about it? So what they did, so basically they have the data like this, right? So let me copy this quickly for you guys. So they have data like this. What they did this with data, I'll copy it here. What they did with this data, they kind of inserted or added few things. Okay, so what they did, they divided the JSON file into two formats. First is a schema, and second is data. So when you see here, this is your original file. From this original file, what they did, they just take out the schema. Schema means this particular column here and the type of this column, this particular column and the type of this column, this particular column and the type of this column, right? And they give something called tag number here. Okay, and then what they did something very interesting. So obviously they have stored this schema once, only once. Okay, and then what they did, into their data, they have some reference to this schema in some way. So they store the schema at one place, and into their data they have just some references to these tags. So what they will do, something like this: 1 and Martin. Now from this one we came to know two things. This Martin is username, and this is required, and this is string, because this is one. Okay, now let's see. Obviously this is one on very high level, but let's jump one level deep, and we will come to the size later. So this particular data, same data, what they did, they stored like this in thrift protocol, thrift compact protocol. What they did, they stored the tag number, they stored the schema somewhere, and into each row of data they just inserted the tag number. So here if we see, this data will look like this. This data, this particular data. 18 means what? 18 means that the field number is 1 and the type is string. 1 and string. Then what we can see here, that length is 6. Length is 6 for what? For the name. Now this length is 6 and the field tag is 1. So what we can for sure we can see here that this field tag is relevant to here. So the Martin is nothing but username, its data type is string, and it is required. Okay, now when we go to the next time, we can say field plus equal to 1. It means field equal to 2 or tag is equal to 2. So tag is equal to 2 means it is this particular number is, yeah, oh sorry, I missed one point. Everything is hexadecimal. Everything is hexadecimal, okay. And when we can see here that they stored this number is number here is signed integer, and what we can see here, the number is 1337. See, I don't want to go into detail, but I'm just telling you one thing, that I want to focus on only one thing here, because I'm not hexadecimal expert, or I'm not expert in this field, but I want to focus on one thing, this thing, that which with every data it stored the tag, and there is the what they can say, they inserted tag somewhere here, and the tag has been a relation with the schema. This is thrift protocol. Now see the benefits. The data which is stored in 60 bytes has been stored into 34 bytes. One more thing which is applicable here, that we are not passing schema information, we are just passing tag information, right? Now this is thrift, which is developed by Facebook. Same thing, Google work in the same year or maybe nearby. They call their algorithm as protocol buffer. Okay, in protocol buffer, they are almost doing the same thing. They have tag number here at the end. Facebook has tag number here in the beginning. Now, what these people are doing, Facebook Thrift was doing something like field 1 and then 1 plus equal to 1. They are adding new field, something like this, right? Field 1, f is equal to 1, f is equal to f plus 1, f is equal to f plus 1. Again, in this way, Thrift is working. Now, what Google did or protocol buffer did, they just stored the tag number as it is. So, for example, when we talk about, sorry, where was I? Yeah. So whenever I talk about 0A, it means this is field 1, length is 6, right? This is field 1, length is 6. Now this particular data is hexadecimal. It means Martin, and this is tag 1. So this is tag 1. Tag 1 means what? Username and string and this required field. Same way it worked, but the only benefit what we got here, that it again compresses from 34 bytes to 33 bytes. So JSON was doing serialization 66, 34 is for thrift, 33 is for buffer, right? These two techniques use tags. Before I jump to Avro, one thing what you can see here, that these two techniques are based on tags. Now let's say if I have a database, I have 1, 2, 3 columns. I want to add one more column here, fourth column. What I need to do, I need to update the schema here. And I need to add a new tag number there, right? Makes sense, right? And so it means every time when I'm adding new field, I need to update my schema with a new tag number. Or we can write some script which can add a new tag number, but obviously we need to do something manual. So this is the problem with tags, right? So now people in 2010 come up with a new approach called Avro, and this is where we need to focus on next 15 minutes. So in 2010 or 2009, people come up with a new approach, okay, and they call this particular approach as Avro. Now what Avro was doing, Avro is almost doing the same thing. Okay, Avro is almost doing the same thing. So they have the same thing, that this schema, right? So they stored their schema into some schema file, and then they serialize it using the same way what Thrift and Protobuf was doing. But here, the most important thing, there is no tag number. Right? So what these people are doing, that they are matching the records in the way they are coming. For example, if they say Martin here, right, the length is 6, they are matching this record with the first record. Then they are matching the second record with the second in the schema, third with the third in the schema. So it means they are not storing tag number or anything about the schema anywhere. So it just, they are matching the name with the values, and that's where they are 32 bytes here. Okay, so this is how, see why I covered Protobuf, Thrift, because I need to show you how people started thinking about it. So here in Avro, we are not storing any tag number. So Avro is not tag based algorithm. So Avro is a data serialization algorithm, but it only uses the order in which the field occurred, and it will match the field or map the fields with the schema on one by one basis. Okay. One more thing about Avro. So let's say, okay, so okay, let's see one more thing about Avro. So whenever we talk about Avro, So Avro file will have majorly two blocks. The first block is called header, and then we have the data blocks. So in Avro file, we have header block and then we have data blocks. Okay, whenever we talk about header blocks, header block will have three types of information. The first information is the file metadata and file schema and the compression codec, in which what compression codec we have used. Then the second most important information is sync marker. Sync marker means from where we can break the record. Okay, this is good. So let's see how Avro files looks like in practical. Okay, yeah, one more thing. These blocks or data blocks are stored in binary, and the schema, Avro schema into header is stored as JSON. Okay, and we are talking about big data here. So although JSON is not very efficient in serialize, still for millions of records, we are only storing JSON for one time. So let's see how Avro looks like, and then we will go for the practical. Okay, so this is how your Avro will looks like. So when we can see here, 1 second. Okay, so what we can see here, the first thing is obj. The second thing is avro.schema, right? Avro schema means in which the record will appear in the binary format. The third thing is avro.codec. Which codec we have used? We have used Snappy here. And the last column is the sync marker. Okay. So now, before we jump to practical, let's see how Avro stores the data and how Avro files looks like. So Avro files store the data into object containers. So this, in a very simple term, this full thing is called object container. In object container, what it says that Avro includes a simple object container file format. The file has a schema, and all the objects stored in the file must be written according to the schema. So what it says that this schema is applicable to each block. Every record follows this schema, and this is guaranteed. When we talk about Avro, this is guaranteed. Okay. And one more thing, what Avro stored, that how blocks are compressed, that is compression codec, and then sync marker, and yeah, this is what. One more thing about Avro is row-based storage format. Oh, yeah, I'll come to it. The question is, does Avro supports Schema Evolution? I'll come to it and I'll cover it in a lot of detail. So Avro is a row-based storage format for Hadoop, which is widely used for serialization platform. We know about it. Avro is to schema in JSON format and make it easy and interpreted by any program. So the schema is stored in JSON, data is stored in binary, right? Data itself is stored in binary format and compact. Okay, one more important thing about Avro is language neutral. So we can use Avro in any language, right? It doesn't matter whether we are using Python, we are using Java. Avro, the data which is serialized by Avro can be written. Let's say we write Avro using Java, and we can read the same data using Python, because Avro is language neutral, right? The feature about Avro is Avro support data schemas that change over time. So what this particular line means, and this is the most important thing about Avro, that Avro supports schema evolution. Now, schema evolution means four things. We can add a field, we can delete a field, we can add new columns, we can change the data types. So this is where the schema evolution comes in picture, right? Whenever we talk about schema evolution, we talk about two things: backward compatibility and forward compatibility. So let's talk about, so we know about Avro, that Avro is row-based storage. So row-based storage means what? Whenever you want to read or write the full row at a time. We know about row-based storage, right? So before I jump to schema evolution, let me cover this thing. Okay, so now where we will use Avro? Avro will be used somewhere where we want to write and read the full rows at a time. So where we will read and write the full row at a time. So let's say we have a source system, then we have your Hadoop or SDFS, and in SDFS we have different kinds of zones, right? We have landing zone where the raw data will come, we have processing zone or something like this. So if we have some data coming from the source system, first it will go to where? Landing zone. It will go to landing zone. So it means, and in landing zone, we want the raw data in the raw format. We want raw data in the raw format, right? So one thing is very clear here, that in landing zone, we want some row oriented format. And we want the format which is easily serializable. So for the landing zone, Avro is the right format, right? Because landing zone, we want everything, then we can, let's say we have 100 columns here. We just bring 100 columns here. If we want 50 column into processing zone, we can filter it here. Because in future, we may need 70 columns into next processing zone. So it's always better to push everything to the landing zone. Okay, so Avro is the right candidate for the landing zone. Okay, and so one more benefit is, okay, landing zone we know, and data from landing zone is usually read as a whole for the further processing, but by downstream systems can easily retrieve table schema from files. Since Avro has a schema inbuilt into it, so downstream system can easily read this data, right? Avro data format has been successfully, okay. So basically schema is written into JSON format, so it's easy to read, you know, and schema change or schema evolution can easily tackled in Avro. Okay. Okay. Now for the next 10 minutes, we will be focusing on schema evolution. So whenever we talk about schema evolution has two things which we need to keep in mind. So let's say we have two schemas or two applications, application 1 and application 2, right? Application 1 is old application, application 2 is new application, right? So, and application 1 has schema 1 and application 2 has schema 2. It means schema 1 has 4 columns, schema 2 has 5 columns, something like it. Both are same data, both are table 1 only, but this schema has been changed in newer schema. So we talk about two things here, forward compatibility and backward compatibility. So what, and Avro supports both compatibility with some rules. So what Avro says, with Avro, forward compatibility means that you can have new version of schema as writer and old version of schema as reader. New version of schema as writer. So it means if we have a writer here, so I'm talking about backward compatibility. So what backward compatibility means, that you have new version of schema as writer and old version of schema as reader. So it means what? That means that you have new version of schema as reader and old version as writer. One second, new version of schema as writer and old version of schema as reader. And backward compatibility means that you have new version of schema as reader and old version as writer. I think this is complicated. I have some other thing here. Okay. Backward compatibility in very, very normal terms means newer code can read the data written in older code. It means newer schema can read data which is written in the older schema. This is called backward compatibility. So it means, let's say we have 5 columns into schema, new schema, and we have only 4 columns into older schema, and we read this older schema using newer application. It should not fail. It should somehow evolve to put some default value for this 5th column and give the data like this, 1, 2, 3, 4 from this column and some default value for the 5th column. This is called backward compatibility. older code can read data from written in the newer code. Guys, can you please mute yourself? Older code can read data that was written in by the newer code. It means, let's say we have 5 column here and 4 column here, and we want to read data 5 column from here. Again, here we have only 4 columns. Here we have 5 columns. In older application we have 5. In newer application we have 5 columns, 4 columns and 5 columns. So when we read data from here, we only want 4 columns. So it means we will ignore the 5th column. Simple. So it means backward compatibility and forward compatibility means this. Now the question arises, how? So we know Avro supports schema evolution in the best possible way in the market. So Avro is the, what we can say, supports both backward compatibility and forward compatibility. Now the question arises, how it supports both compatibility. So whenever we are talking about schema evolution, we talk about rules, right? Schema evolution rules. So every compatibility has schema evolution rules. So when we talk about compatibility, we have 2 compatibility, backward and forward. To maintain the compatibility, you may add and remove field that has default value. Okay. So what we talk about, add, remove the field from any schema. So whenever, what compatibility evolution rules or schema evolution rules means, whenever we add a new column, to the existing schema and we want to read it, we always need to default the value. So the first rule for schema evolution is, if you want to add the column, always have the default value. So what these guys are saying, if you were to add a field that has no default value, no reader wouldn't be able to read the data by the old writer, so you will break the compatibility. In very, very simple terms, what these guys are saying, that let's say you have 4 columns in the old schema, you have 5 columns into the newer schema. If you don't have the default value for this 5th column, how your program will come to know what is the value for it? So you will break the compatibility. Right? Or if you were to remove the field that has no default value, old reader wouldn't have, so this will break the backward compatibility. But if you remove the field that has no default value, old reader wouldn't be able to read the data. For example, let's say if you remove one field, it has no default value and your older schema wants to read the data. Again, it will fail because it won't find the field value for that data. In very, very simple terms, we need to have default value attached to the data if we want to have the schema evolution done, right? One more question. In programming language, null is acceptable default for any variable, but in Avro we cannot accept null as a default value, right? So now the question arises, how do we need to assign null value into Avro? The easiest way is to create the union type. We'll cover it in practical, but this is the easiest way. Okay. Yeah, in Avro we don't have optional and required markers. So when you see here, into thrift, right? Into thrift, what we have optional and repeated. But when you go for required, optional, repeated, required. But when you go for Avro, do we have anything for required, optional? Nothing, right? So we don't have required, optional, repeated into Avro. Okay. Okay. Now changing of the data type. Okay, we can do few things. We can add a column, we can remove a column, but changing the data type is possible. But if it is, for example, if we change int to long, what it will do? It will easily encountered, right? It can be easily tackled because long is kind of higher storage or higher hierarchy than int. But if we store long into int, if we change long to int, it may truncate the data. That's what it is written here. That data type change is possible. Now the last question, can we change the field name? Can we change the field name? The answer is yes, but it's not preferable. Okay. So because the answer to this question is, and one more thing. So let's say this is your old schema, this is a newer schema, and we have 4 columns in old and new, but you change the format, you change the sequence. So what Avro do for you? Avro just map the name with old and newer column, or old column name or field name with the new field name. So what it is, let's say you write your data using this one, you read your data using this schema, and you just change the sequence of the columns, right? 1, 2, 3, 4. Here also 1, 2, 3, 4. Avro will use the field name. It will search the field name of the writer's schema, and it will match to the reader's schema. This is how the schema evolution works, right? So schema evolution works because Avro is based on field name, not on tag number. So field name is very, very important in Avro. Okay. So this is good. What are the benefits of Avro? Dynamic schema support, union types, serialization and deserialization with human readable JSON, highly efficient. Okay, schema versioning is supported. For example, we can have multiple versions of a schema at the same point of time. Let's say we have 5 columns in one schema in the same table. We can have 4 columns, we can have 3 columns, we can have 7 columns, and we store this version in schema registry. I will be covering it in the section, but this we can have the same. We can have different version of a schema of the same table or the same file at the same point of time, right? So this is what Avro looks like. Now let's cover some practical thing. One more important thing before I jump to practical. So Avro store is a schema in a file called .absc. So this is the schema file for Avro. Okay, now let's see how it looks in practical. Okay. So let's clear this for 2 minutes. So what I'm doing here, I'm doing very, very simple thing. Okay, so what I'm doing here, I'm reading, and this is, again, I can remove, I can comment it. I don't want it. Okay, so what I'm doing here, I'm reading one file called zipcode.json. Okay, and this zipcode.json is here somewhere. And to, 1 second, see where it is. See users and test data, right? Yeah, test data. So what we can see here, this is my zipcode.json. Let me open it. So it will take time anyways. Oh, wait. So this is how my zipcode.json looks like. Okay. So what I'm doing here, I'm reading data from test data, zipcode.json, right? I'm reading this file. The format is JSON, the path is this. You can remove this part if you want. I don't want to cover it. And then I'm showing it. And one thing what I'm doing, let's do one thing first. Let's remove this. Yeah. And what I'm doing now, I'm just writing this data. I'm just writing this data and into Avro format, into my, let's say I want to create a new folder. So when we go here into test data, we don't have zip test 5. Right? Let us create a new folder called zip test 5. Simple. We are reading a JSON file and we are storing that JSON file into Avro. Okay. One more thing which I did here, because Avro didn't come by default by Spark application, right? So what you guys need to do, you guys need to add a jar, external jar, The external jar is Spark Avro, your Scala version, and your Spark version. Spark Avro, your Scala version, and your whatever. See, now it's simple, right? So what I did here, I just go to Google. This is one second. So this is where I downloaded it. So I just go to Maven. I go to Spark Avro 2.4.4, and I downloaded this jar, and I added the jar to my external libraries. This ID is Scala ID. Okay. So, and then it started working. Okay. So that's good. So what I did, I read the file, JSON format, and I'm storing it into a new directory called test this1. And if I go from the beginning, I'm doing very less thing here. So let me uncomment this part as well. So I want to log only errors. I created a Spark session. I don't need this part as well for the time being. And then using that Spark session, I read the file and I give the format as JSON. I give the path. I just show the data for you guys, and then I store the data into Avro. Simple. Let's run it. Run as Scala application. Let's see. So it will be very quick. So let's see. So this is how you need to write. See, again, not a very rocket science thing, and it's very easy to use, right? Let's see here into your this one. We don't have zip 5 created till now. I'm just refreshing it. So it's still running for me. So I'll just refresh it. Let's wait for 2 minutes. Okay, so it ran for us. So what it did, it read the JSON file. So my JSON data looks like this, right? My JSON data looks like this. I have 4 columns: city, state, zip code type, and zip code. So this is my JSON file. It is stopped. It means my application runs successfully. Now let's go here. What we can see here, we have a new folder created, zip code test 5. When we go here, we have a new file created, .avro. Now let's do one thing. The size of this file is 231 KB. Now let's see the size of our raw file. The size of my file is 11 MB. So see, and again, this is just a small data. My 11 MB file has been compressed to 231 KB. Okay, now let's see this data, how this data looks like. So what it says, it again saying that this is Avro schema, this is header, right? In header, we have this type. I will copy this thing for you. Till here. So I'm just copying this schema. Okay, till here we have the schema, right? So I'll just copy this, and then we are saying which codec we are using. We are using Snappy for the record level compression, and then some other stuff, right? But what we can see here, this is our header and this is our data. Data is stored into binary format, which won't make sense to us. Okay, now let's start one more thing. This is our schema, which I copied from this file. So what it says, the type is record. It gave some name to our schema, and then it gave some fields to us. Now let's see how those fields looks like. So it says your field 1 is city, your field 2 is state, your field 3 is zip code type, right? Your field 3 is zip code type, and your field 4 is zip code. So this is your schema. Let's do one thing. Yeah, this is your schema, right? So this schema is take that schema from here. So what Avro did for us, so Avro did the same thing for us. It takes city from here, it gives a string, everything is stored as string, but it inferred the type as long here, see, right? So this is how Avro stored the schema. Now, I told you guys that we can also store the schema in .avsc files. Now let's do one thing. Let's save this file, save as, into, let's say, test data my schema.avsc. Okay, and save it. Now let's go to test data. Where is that file? Yeah, this one. So this avsc file, right? Now let's use this file to give schema to your JSON file or to read data. Okay, so what we need to do here, so what we did here, the same thing. Okay, let's do one thing. In fact, let's do this thing first. So what we are doing here, let's use this column, this file, Control A, Control C. Okay, to use the schema, you need to use org apache avro.schema. From that schema, you need to use parser, right? In the Spark I'm talking about. And then you need to give your schema avsc file here. So what you need to create a new variable called schema whatever, and then you need to create a new class, a new function called schema avro whatever, and then you need to parse the schema. So now this particular, this is what? This is avro schema. The type of this val is schema. So it means it is avsc file, and the type of this variable is schema. Now, very, very simple. We need to read the avro file. Right? And using which schema? Using this schema avro. We converted that schema into toString. Now let's say we want to read the same file what we wrote, test5.this one. Simple, right? And let's do one thing. Let's store that file as JSON again. And let's store that file into 6. So what I did, I'm reading the avro file now. Using avsc file, first I converted that avsc file, I passed that avsc into schema, and then I gave that schema into option field into my Spark read, and then I'm saving that file into JSON file. Okay, overwrite whatever. So it means that I'm overwriting everything on the directory, but since my directory is new, it won't overwrite anything. So let's run it. Let's see if it is working or not. Let's see if this is working or not. So what I'm doing, I'm reading the avro file and I'm giving some schema to it, avro file. Obviously, see, schema has been attached to avro file, but I'm just using it because I want to tell you one more use case. And then I'm writing, then I'm showing it to you guys. And then I'm writing to zip code.test.6, and I'm writing in JSON format. Let's see if this is working. And then we will do one more interesting thing in 2 minutes. Let's see if we don't have zip code _6 here, right? It will create for us. So it worked. Okay. So what it did the same thing. This is the data came from avro file because we just read the avro file here. And then we see here zip code created. And again, the size is again increased because we did it in JSON format, right? Now let's do one thing. Let's open it. What we can see here, it's very simple. What this guy did for us, it again did city, state, zip code type, standard, nothing very fancy. It just read the avro file, assign some schema to it. Now let's do one fancy thing. Backward compatibility and forward compatibility. Let's do that thing. Let's do one thing. Let's delete one row or one column from here and save it. So what we did, we deleted the last column called zip code from our schema, right? And we saved that schema into my schema.avsc, and we used the same here. And let's read it. So what it means one thing. What I'm trying to prove it here, that my source has 4 columns and my target has 3 columns. Ideally, it should not fail. It should support the compatibility. Let's prove that part. So let's run this now. So I'm using overwrite. So it means this file will be overwritten here in 2 minutes. Okay, let's see. So ideally, it will only show me 3 columns here. Okay, let's see. So ideally, I'm proving the compatibility, how schema evolution is supported. Okay, so what we can see here, that city state partition, city state zip code type has been read, but the fourth column zip code is not read here. So it means one thing is supported, that if one schema has more columns, other schema has less column, it is supported. Now let's go here. This is your new file. Obviously one column is gone, so the size is less. Now let's do one thing. Let's go here. Let's see here. So we can see that data type for what I can say, the zip code has been removed. Now let's do one thing. Let's do one thing, guys. Okay, so let's add that column again. Control Z. Yeah, that's what I'm doing. So let's add the column again. No. Before adding the column, I need to prove one more thing. I added this column again, but I added this here into the beginning. Okay, and let's save it. Let's run it. Now let's see what I did. I just reformatted, moved the column here and there. Ideally it should work, but let's see if this is working or not. So the first case, I removed the column, it worked fine for us. The second case, I just moved the column here and there. But I moved the last column to the first place, so the zip code has been moved to the first column. Let's see if it's working. The third thing, what somebody else is suggesting, add a new column. I'll try to do it. Okay, 1 second. Okay, let it run. Meanwhile, let me do one thing. Prepare the next use case, okay, to delete the column. Test data, I've already done it for you guys. So zip with default. Okay, 1, 2, 3, 4. Anyways, so I'll just copy this. In fact, let's open this here for 2 minutes, and let's see if the okay. So what we can see here, that when we move the zip code to the first, it again worked perfectly fine. How it is working? The same thing what I explained. How I explained to you guys, something like this. This way. So this is our old schema. Right? In which we have column into this format, this structure, or this order. Into a new schema, we have just reshuffled the column. But what Avro do for us, Avro just look for the name, it maps the name, and it gives the result. So what Avro did for us, it just mapped the result, again give zip code type, city, state, zip code, whatever. But it worked for us. Now when we go here, zip code again the size is increased, and when we see the data again here, it again zip code type come first. Okay, now let's do one thing. Let's do one more thing. Let's add a new column. Let's say this one. Okay, let's close these files first. No. Close this as well. Close this as well. No. Okay, let's open one file which we are working on. So this is our my schema, right? So let's open this file. Okay, so now let me add one more new column called zip code data. Or let's say called country. Okay, and I don't want to give the default value. Now let's see if this is working. So what we did, the same thing, zip code type 4 columns. We want to add a new column. So let's run it. This time we haven't given the default value. Okay, so what we did, we added a new column, but we haven't given the default value. Let's see if it's working. Ideally, what I proved in theory that it should not work, but let's see if in practical it's working. Okay, so the new column name is country, and the type I have given is basically it should not work, but let's see. Okay, it didn't work. Why it didn't work? It says that okay, found top record, it means the top record found, and then it is expecting the field country, but it didn't found. So basically what it says that it is not able to resolve the schema or the value for the new column called country. Okay, let's do one thing. Let's add one default value from like this. So at the default value, you can say this one. For now, I will say here this one, and for a timing to make it more sensitive, I'll say country code because it is long, right? And let's run it now. So one thing is proof that if we don't have the default value, schema evolution is not supported. To support the schema evolution, you need to give default value. How to give default value? In AVSC file, you can give default value like this, 1, 2, 3, 4. Okay, using default keyword, and then see, it's a JSON format. In simple terms, it's JSON format. In JSON format, you need to use a new tag here for the default and into the value. Now let's see. Okay, so ID perfect, it worked this time without an issue. It gave us the country code as a new column and 1, 2, 3, 4. When we go to our zip code.6 directory, you can see the size has been increased again by 2 MB. And when we open this directory here, open this file here, we can see a new column added, zip code.type. Okay, so see, again, there can be a lot of permutation combination which we can do, but I would prefer that you guys do at your home. One thing was I want to prove here that in this way, Avro supports schema evolution. The one of the most important thing about Avro is Avro schema don't have any tags. Don't have any tags. So it means let's say every time when you are writing the data, every time when you are writing the data means you read the data from some database. It has 3 columns, and when you read the data here using Avro, so you will have some schema attached to it, let's say S1, and then you have data in binary format, in block format, into your object container. So once you read the data from database using some Avro reader, it will give the schema at the first in the JSON format, right? And it will give the data. And then once you read this Avro file, so this is your writer. Writer means Avro writer. Okay, so in object container, you have everything, your schema, your blocks and everything. So this is your object container. Okay, and once you read this data, once you read the data, you already have schema attached to the data. You already have schema attached to the data. So reader already know the data, already know the schema. Okay, so every time when you are writing the Avro file, schema will be new. Let's say after 2 days, you attach one new column. So once you again write a new Avro file 2, how the schema will look like? Schema will have 4 columns and your data blocks will have 4 columns. So this object container will have new schema and new records. So basically what I'm going to prove here, that as a Avro supports schema evolution because we don't have any tag numbers. So let's say you have a tag number. Let's say in Avro we have tag number. So in tag number, can we assign a tag number here 1, 2, 3, 1, 2, 3, 4 or 1, 2, 3, 4, 5? We need to write our own logic, or as an administrator, we need to add a new tags to our schema every time. That's where the tags have some issues. But Avro says, guys, I don't want to go for tags. I will go for the field names. I will go for the field names. And I will match the old schema with the new schema using field names. When you add a new field name, you need to give a default value. When you delete a new one field name, you can delete it as far as your old schema don't have that field, right? This is where the whole compatibility or schema evolution comes in picture, right? Let's go here and let's see if I missed something. Schema. Okay, one more thing which I need to cover. The whole knowledge what I gave in last 30-45 minutes. The book written by Martin, Klipman. Designing data intensive application is a very, very good book. It's not about Avro, but it has one chapter dedicated to Avro. if you want to discover more, do buy this book, or do read this book. This is very, very good book for data intensive applications, right? See, Avro is not a file format, it's a file format plus serialization and deserialization framework. With regular old scheme files, you can store complex objects, but you cannot manage to, but you have to manage the process. Avro handles the complexity while providing other tools to manage the overtime, like the same thing written in other language. Avro is well thought out format which defines the data schema in JSON, and it supports block level compression as well, right? Yeah, serialization and encoding are both things. Both are same things. Okay. I think this is all. So this is all about Avro. I think tomorrow we will be covering Parquet in a lot of details, or and then we will be covering ORC.